Yeah. Wow. Well, glad you guys made it. Nice shirt. I was wearing that shirt like Saturday. So very nice. Way to rep the math education department. So yes, as you should. All right, let's get started. Who'd like to offer a prayer for us? Thank you. Amen. Thank you very much. Michelle, I forgot to start it recording. Okay, thanks. Okay, a little information. First midterm exams coming up this week, starts on Thursday. So you have Thursday, Friday, Saturday, and Monday. Monday is a late day. So if you take it then, it's going to cost you money. So don't take it Monday. Okay. Just take it Saturday and send me the money. Okay. It covers everything up through 3.3. There's no calculators or notes, etc. So it's you, the test, a pencil, and scratch paper. So that's it. Please make sure you know how to do all the problems in the practice exams in preparation for the exam. There's 3 practice exams up there, so make sure you go through all of those. You don't have to do them all. If there's a problem that you know for sure you know how to do, don't spend the time working on that. Go work on the ones that you're not confident you know how. But you should make sure you know how to do all those problems. If you do that and you know how to do the homework problems, you're confident in with the ideas we've talked about in class, you'll do fantastic. So questions? Any questions specifically about the exam? Yes, Tyson. Yep, there's a content tab called, I think it's called review materials or exam review materials. So they're on there. There's a couple, what's the word? Sheets, review sheets on there also. Okay. Other questions specific to the exam? Yes. You can write on the test. So, but you might want to bring scratch paper too. So, yeah. Any other questions? Okay. Today we're finishing up 3.3 on inverse matrices, and then tomorrow we will spend the day reviewing for the exam. So I'll be pulling up some of the problems on those practice exams, other things. If you have questions, so one of your assignments over here is work on a practice exam before tomorrow and come with questions if you have any questions so we can talk about those. Also a note on the written homework that's assigned today, finishing up 3.3. We're going to make it due by the end of the day on Thursday. Okay, it's not due tomorrow in class. Okay, just the end of the day on Thursday. So yeah, otherwise it's a pretty tight turnaround. Okay, all right, let's get started. Any questions from the reading or the video that I need to be sure to hit today on inverse matrices? Yes. Is invertible? Okay. Okay, so the question is, how do you prove the identity matrix is invertible? So if we have an identity matrix, okay, can you find a matrix you can multiply the identity matrix by and get the identity matrix? Matrix, yeah, go ahead. Yeah. So one of the ways to prove it is, since the definition of of an inverse matrix is if you can find a matrix that you can multiply by that matrix and get the identity. So we can go right back to the definition and say, well, if I can find one and show that this times another matrix is the identity matrix, then I know this is an inverse. This has an inverse, or it is invertible. So what matrix could I put here? The identity matrix. You could have another identity matrix. Just square it. You could think about squaring it. So the identity matrix times the identity matrix is the identity matrix. So yeah, IN times IN is IN. So we know it's invertible because we've actually found a matrix that we can multiply by the identity matrix and get the identity matrix. So that's one way to show that a matrix is invertible, is to actually find one. Usually usually if we have to prove something's invertible, that's usually not the way we go. It depends, but it might be hard to find one. Usually there's other ways, like to show that each of the columns is, there's a pivot, it's a square matrix and there's a pivot position in each column. So we could also prove it that way. No, so yeah, there's lots of different ways to do this. And in fact, when we'll have a slide where it shows a lot of different qualities, the invertible matrix theorem, and you could use probably about any of those to prove this. So yeah, there's not just one way. So thank you, nice question. Okay, any other questions about the content that we need to be sure to hit today? Okay. Let's start off. We've got 4 problems of the day. So first one is find the inverse of the following matrix. So you should have had some practice in doing this for the WebAssign. Write down, number 2 is write down the elementary matrix that corresponds to the first row operation you used in the number 1. So answers may vary depending on what you did for the first row operation there. And use the inverse from above to solve the following equation. And then there is an equation down there where you have matrices A, B, and X. And you're going to try to solve that for X, okay? So let's take 10 minutes or so. You guys can work on this. You're welcome to work with your neighbor, okay? If you got questions, go ahead and raise your hand. Okay, take about 1 more minute. All right. I'm going to start with number 1 over here. So a lot of you did really well at knowing you went right to went the right strategy. You knew exactly what you needed to do, either from the reading or the video. You came and you thought, oh, I need if I'm after an inverse, I'm going to augment that with the identity matrix. And then you row reduce the left-hand side. You're row reducing the whole thing, like you're doing the row operations to the whole matrix, but you row reduce the left so that it eventually looks like the identity matrix. Okay? And one way to think about what you're doing, remember we talked about inverses, we talked about matrices as transformations, and here you're doing you're undoing the transformation on this side to get it to the identity, and you have a record on the other side of all the transformations you had to do to undo this transformation. And so this record ends up being the inverse matrix. So we could actually multiply those together and check. This is, I would strongly encourage you to check this on when you have a problem like this, which there almost always a problem like this on the exam. You have to find an inverse. Check it to make sure it actually works. So 112, 201, 022. You can actually multiply it by, that's dying. A -1, 1, a half, a -2, 1, 3 halves, 2, a -1, a -1. So actually do the multiplication. A -1, a -2. So I have a -3 plus 4. That gets me a 1. There I have a 1 plus a 1 minus a 2. That's a 0. And you can just keep going through to check, and you better get the identity matrix over here. If you don't, then you did something wrong when you were row reducing. So, okay. Bit of a bear, okay? Finding inverses, especially of larger matrices, it's not easy. Takes lots of work. I mean, even for computers, okay? If you have a really large matrix, if you have I think it was a 50 by 50 matrix, takes like at current speeds like 100,000 years for the computer to do it. That's like crazy how long it would take a computer to find the inverse of a really large matrix. So small ones were not too bad. So, okay, questions on this? Okay, let's jump to number 2. So the first oh, this person swapped rows for their first move. Other people did a different move. So your answer might be different here. Is you might, if you take the first row and multiply it by a -2, and then add to make that 0, that's what some people would have done. This is a swap. So depending on what you did, this answer might be different. So Rochelle put her answer up, and it looks like that's what you did, right, Rochelle? Yeah, right, you didn't swap. You multiplied the first row by a -2 and added it to the second row. So this is the elementary matrix that captures that. So if we put that original matrix up there, can't see it, 1, 1, 2, 0, 1, and 0, 2, 2, and we do this multiplication, what do we get? Well, I'm going to get 1. So if I multiply this times that first column, right? I'm dotting that first column, the first row to the first column. I just get a 1. Then this times this first row, second column. These zeros are going to wipe out anything here. I just get a 1 times the 1 times the 2, everything else is 0. That 1, 0, 0 is just going to duplicate my first row. How about the second? Now the second row here, -2 times 1 plus a 2, and then I get 0 times 0. So I get a -2 plus a 2, so I get 0. A -2 times a 1 times a 0 and 0, so I get a -2. -2 times 2 is a -4. 1 times the 1 is 1. 0 times 0, so I get a -4 plus a 1, that's a -3. And now the 0, 0, 1, it's going to do a similar thing to that one that the 1, 0, 0 did. When I multiply this, when I do the dot product with this row and each of these columns, I'm just going to reproduce that bottom row. Because I'm going to have 0, 0, 1, 0, 0, 1, 0, 0, 1. So I'm going to end up with 0, 2, 2. And that's exactly what you'll end up with if you multiply that first row by a -2 and add to the second row. So this is called an elementary matrix. We'll talk a little bit more about these in a minute. Okay. Questions here? I don't know, some of you are shaky on this. We'll come back to elementary matrices in a minute. Okay. 3. So 3, you were supposed to use the inverse that you found on number 1 and solve that system. And so how do you solve a system AX equals B with the inverse? Well, if you know the inverse, you can multiply A inverse by this side and A inverse on this side. We're doing we're putting it on the left on each side. Okay, you have to pay attention to where you put the matrix because it's non-commutative. So A inverse times A is just the identity matrix times X, and that of course is just X, and you get A inverse times B. So if you can just calculate A inverse times B, then you get what X equals, and B was this matrix here, I'm sorry, was this vector here. So multiply the inverse times this, you get 8, 1, 2, 2. Okay? I know those weren't a lot of fun numbers, but you'll see why we did that later on. Okay, any questions on this? Okay. Finally, we have this equation. Here you have representing each of our matrices with a letter, and then we're trying to solve for X. So the original matrix was this. I'm sorry, the original equation was this. And so this person thought, let's multiply A inverse on this side to get rid of this A. And so that's where this A inverse came from. And then we had a B, so multiply B inverse on this side. So now we have an A inverse, B inverse, and now we have X. Now you've got to start multiplying things on the right side. So I have B inverse here. Well, to cancel out the B inverse, I want to multiply by B. So the multiplying by the inverse is what you would, whenever you would be dividing with, when you're solving linear equations that you're already used to in algebra, there's no division in, I mean, technically there's no division in matrix algebra. There's only multiplying by the inverse. So you're undoing a multiplication. We just do it with another multiplication. So multiply b on both sides. The b times the b inverse becomes the identity. Multiply by a on the right of both sides. That becomes the identity. So we get x, but we can do some simplification. So we have an a times an a inverse. That becomes the identity matrix. We can distribute the BA out. Be careful to keep the BA on the right-hand side of both those expressions. And then we get a B inverse B that simplifies to the identity. So we get this. Can't we simplify that further? Sure, looks like we should be able to. What if we just swap the order of that B and the A inverse? Then you'd have AA inverse over here, BB inverse, and it would that would all simplify down to the identity. Wouldn't that be nice? Yeah, if you did that, you'd be wrong. Okay, why is that incorrect, Carolyn? That's right. You have to multiply them in the right order. The matrices matrix multiplication is not commutative, okay? Unless you knew beforehand that these were commutative, then you could do it. But if this is just a general A and B, then you don't know. So you have to keep it this way. You're not sure if it's going to be equivalent to what you'd simplify it to. Yes? Oh, that question was, can I explain how to distribute again? Yes. So let's go to, like right here. Is this a good? Oh, okay. So, yeah, so here we have I plus A. I don't know if it went away, but let's just go right here. We've done some multiplication on the left. We've done some multiplication on the right. Actually, here, let's go to this one. And we can distribute this B times B inverse times A inverse. We can distribute this in. But that B inverse times A inverse, we have to be sure to keep on the left-hand side of each of these. Okay, we're doing left distributive. So it's going to be B inverse A inverse times I, okay, plus B inverse A inverse times A, right there, and then we still have the BA. Okay. Now at this point, BA inverse A inverse times I, there's a simpler way we can write this. What do you think, Carolyn? Or is it Caroline? Caroline. Okay. How about someone else? Help us out here. Yes. That's right. So the multiplication, this is basically multiplying a matrix by 1. It's multiplying by a matrix that times another matrix that doesn't change anything. So it's equivalent, it kind of has the analog of being 1. So you could just rewrite this as B inverse A inverse and drop the I, because now you don't need that anymore. You still needed it here. It was worth serving as an important placeholder for you, right? You can't just drop it. Okay. Yes, Madeline. Isn't B inverse? She said, isn't B inverse A inverse? Isn't that AB? It's not AB, but it's AB inverse. Yeah, so it's not equal to AB, but you could, sometimes it's nice to be able to write it this way. Yeah. So, right. Nice connection. Okay, and then this we can simplify to the identity matrix, and then B inverse times the identity matrix is just B inverse. And then we have BA. So if we distribute this in, we're going to be sure to keep that BA on the right-hand side of each of those terms. So B inverse A inverse BA plus B inverse BA. Okay. Caroline, does that help? Okay. Thanks for asking that question. Okay, other questions with this? Okay. Oh, that was number 4. Great. Okay. So elementary matrices. This is from the slides that you saw on the video. So as I mentioned before, an elementary matrix is one that does the same thing as a row operation. And in practice, we don't calculate these, although, as I mentioned in the reading notes, it's good to see if you can construct those because it helps you make sure you understand matrix multiplication really well. Each of the row operations has a different, kind of a different model. This E2 here will that'll change the order. That's swapping the order of the rows. This first one is adding a multiple of one row to another row. And then the last row operation is multiplying one row by a non-zero constant. And that's what E3 does there. That would multiply that third row, the third row by 5. Okay. So in practice, we don't calculate elementary matrices to find inverses, but it's a really nice thinking tool. Mathematicians would say it's a nice theoretical tool. However, they're valuable in making sense of statements, so elementary matrices are. So here's a nice important theorem that uses elementary matrices. A theorem in the book states that a matrix is invertible if and only if the matrix can be written as a product of elementary matrices. Okay? So if you can take a matrix and factor it down, basically that's what you're doing, you factor it down into a whole bunch of elementary matrices, then it's an invertible matrix. Okay? And it's not only, if it's invertible, you can do that, and if you can do that, it's invertible. Works both ways. Okay? You might be able to convince yourself that's true as we row reduce. Like we'll do this as an example. As we row reduce, I could think of this matrix, this new matrix I have times as the old matrix is now this matrix times an elementary matrix. And now this one is this matrix with 2 elementary matrices multiplied by it. And now this matrix is this matrix with 3 elementary matrices multiplied to it. And then the old matrix is this matrix with 4, or however many I'm on now. I never was good at counting. And eventually I'd get I'd get the identity matrix with 5. Was it 1, 2, 3, 4, 5? Yeah, so I had 5 elementary matrices multiplied by the identity matrix. But if I multiply by the identity matrix, I just get those 5 elementary matrices. And if I row reduce and I don't get the elementary matrix here, the identity matrix, then I can't just rewrite that first matrix as that product because I'd still have this something crazy over here that's not the identity matrix. Okay, so your task with your neighbor, see if we can use this fact to make sense of this statement. How could you use that to reason about the product of 2 invertible matrices? Is an invertible matrix times an invertible matrix always invertible? Think about why or why not. So how do you use that? How do you use what you know about elementary matrices and invertible matrices to think about, hey, I've got a product of 2 invertible matrices. Can I always say that those are invertible? Like that new product of invertible matrices, is that always invertible? So think about that. See what you can come up with. All right. So I didn't get to all the groups, but heard some really nice things. Oh, I didn't want to erase that one. Let me erase this one. So one of the things I heard, so some people are starting to look for counterexamples. Fantastic idea. Especially if you think it's false, then looking for counterexamples is a nice way to go. But some people had the argument that it should be true because if I had two matrices, A and B, and I know that those are invertible, then I could rewrite each of these as a product of invertible matrices, of elementary matrices, sorry. E1, E2, E3, et cetera, to EK. So this might be A. And then I could have, I'll call the elementary matrix over, well, EB1, EB2, et cetera, EBN. So this would be the same as B. If I multiply both of those together, if I multiply all these together, what do I have? I have a product of elementary matrices, and any matrix I can write as a product of elementary matrices must be invertible, because that's what the theorem said. So, if you were asked to prove that the product of elementary matrices, sorry, the product of invertible matrices is an invertible matrix, this is one way you could do it. Say, hey, I know that an invertible matrix can be written as a product of elementary matrices. So you write them both as elementary matrices, multiply them together. Hey, I've got a product of elementary matrices by the theorem. I know that that's an invertible matrix. So, okay, so this is the kind of, even though in practice we don't actually find these, this is an example of how you use it as a thinking tool to reason through things. There's lots of problems on the exam. There are often questions on the exam where you have to figure out if they're true or false, and this is exactly the kind of thing you'd like to work with. Hey, what do I know about invertible matrices? Can I find something? And maybe it's this that might help you out to reason through. So this is, we don't have time to go through all of these. I was going to make some connections, try to figure out why each of these was equivalent. This is a longer fundamental theorem of invertible matrices than you read about. I even put one more on here than was on the exam. It's K there. It's J. You can write it as a product of elementary matrices. There's a few others that aren't on here, like the rank has to be n. If you know the rank of a square matrix is n, the size of the matrix, then you know it is invertible. I'd encourage you, so you can see the task we were trying to do here, is to pick two of these and try to figure out why they're equivalent. If you have one, why do you have the other? If you don't have one, why do you not get the other? So we were going to do that a little, but we're running out of time. Okay. Matrices in cryptography. So I want to end with this example. So if you write down a message, and so I'm going to tell you how to use matrices to encrypt a message. So you write down a message, you translate the letters into numbers. So you can just use the simple space is 0, A is 1, B is 2, C is 3, etc. And then you get an invertible matrix. Try not to use a 2 by 2, but a 3 by 3 or a 4 by 4 or 5 by 5. And then you're going to split your numeric message up into vectors of size n. So if you have a 3 by 3, you're going to take chunks of numbers 3 at a time. So kind of like this here. You're like we've got the 3, the 8, 1. Well, like this one, 53, 38, 46. And to encode the message, you multiply each of those vectors. If it's a 3 by 3, you've got 3 numbers. Multiply that by your invertible matrix. And then you take the person that you're sending the message to, they have to know what your matrix is, and they have to know what your code is. So you send it to them in different ways, because you don't, if they were both intercepted, right, then anyone could decode it. The question is, so this is an example, and then the big question is, how do you decode this? So there's my message, ABCDEF space GH. I use the numeric mapping to get the 1, 2, 3, 4, 5, 6, 0, 7, 8. That encoding matrix, I just picked the same one you guys already found the inverse to over here. And I chunked the message into 3 because I have a 3 by 3 encoding matrix. And I can actually just write that as a single matrix. So the 1, 2, 3 in the column, 4, 5, 6 in the column, 0, 7, 8. And I can encode that by taking my encoding matrix and multiplying it by my message matrix. And I get an encoded matrix. So I could get the encode, as long as I can get the encoded matrix and the, as long as I can get the encoding matrix and the encoded message matrix to the person I'm passing the message to, they can decipher it. But the question is how? How are they going to decipher that message? So just take 30 seconds, 20 seconds, talk to your neighbor. What are you going to do? Okay. All right, any ideas? Who has an idea about how to decipher this message now? Anyone? Philip, sorry. All right, nice idea. If you know the encoding matrix, you can find the inverse of that encoding matrix, and you multiply the message they got by that encoded matrix, by the inverse of the encoded matrix, and that will give you back your 1, 2, 3, 4, 5, 6, 0, 7, 8, and then they can turn that back into letters. Okay, I had one for you to encode, well. So this is the one I was going to have you encode. You already did the first part. So that was the problem number 3, where you multiplied the inverse by 53, 38, 46 to get 8, 1, 2, 2. So the first part of the message was 8 is an H, 1 is an A, and 22 is a V. So HAV is the first part of the message. But the rest was, the whole message was have fun. Have fun is the most important thing to my kids because they include it in every prayer that they say, as they pray that they can have fun. But anyway, one of your assignments on this written assignment is to send a message, a coded message, to someone else in the class, and they'll send it to you. And so you have to write up how you decoded the message that you got sent. We'll put up a video because I know this wasn't enough for all of you. So we'll put up a video on how to do that. So, okay, have a great day.